Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to continue working with vectors in terms of linear algebra, and we're going to learn about the concept of a unit vector in the direction of any vector that we choose. So before we get into it, I guarantee I'll draw a picture on the board. It'll be 100% crystal clear, but let me lead you up to that point. The concept of a unit vector. Everyone watching this has probably taken a physics course at some point in the past or where we have at least introduced the concept of a unit vector. All right, so in the past, we've talked about a unit vector being just a vector that has a length of 1. That's why it's called a unit vector, unit meaning 1. And it really can point in any direction that you want, but traditionally when we talk about vectors, we talk about the important unit vectors, I, j, and k. Those are the vectors that point along the x-axis, the y-axis, and the z-axis. And we need them because we're trying to show where this vector, whatever vector we're trying to represent, where it's pointed. So we say how many units in the x direction or the I hat direction, the unit vector in the I direction, the x direction, how many units in the y direction, how many units in the z direction. So we invent this concept of a unit vector, which is a length 1 pointed along the coordinate axes. All right, so if I had to write that down, it would be called unit vector. The definition of a unit vector is just a vector with length of 1. That's all a unit vector is. Now, the unit vectors that we have been exposed to up until now in math is traditionally the I hat unit vector, the j hat unit vector, and the k hat unit vector. And remember, I can draw an x, y, z axes, and I can show you that I hat points along x, j hat points along y, k hat points along z. We need those to write down our Cartesian representation of a vector. But don't forget that those are just unit vectors, and the general definition for a unit vector is any vector that just points in whatever direction with a length of 1. So frequently, if I'm given a vector, like maybe I have a vector A pointed off in that direction, it has a length, I don't know, maybe if it's a force vector, it could be 15 newtons pointed that direction. And from that vector, I want to calculate what a unit vector would be that points in the direction of my vector A. All right? So that's perfectly consistent with this definition because a unit vector can point really in any direction you want, but it just has to have a length of 1. All right? So if I have, let me switch over to purple here. If I have a vector A, right? And we know that vector A may point in space any which way, any which direction that we want. And from the vector A, let's say we wish to find what a vector would be, calculate a vector that will point in the same direction as A, but only have a length of 1. That would be called a unit vector in the A direction. And we want to calculate that. How do we do that? Well, all you do is you take the vector A that you have. You want your unit vector to point in this direction. But we need to somehow change it so that the vector points along A, but it has a length of 1. So what you do is you take the vector A and you divide it by something, and what you divide it by is the magnitude of vector A, right? And what we get as a result of that, we call that, there's many different ways you can write this. I'm going to write it as A hat. And I'm trying to be consistent with what we have here. I, j, k have a little hat. That means unit vector. So here what we have is a vector that points in the A direction, but yet only has a length of 1. Only has a length of 1. All right, so let me draw a quick picture and hopefully solidify this. So let me say this is called a unit vector in the direction of the vector A. It's very, very useful for many calculations. We'd want to find a unit vector in any old direction that we choose. All right, and so let's look in 2 dimensions first because it's a little easier. So let's say this is the x-axis and this is the y-axis. And let's say that I have some vector A pointed off in this direction. Now clearly this vector A here is not a unit vector. I haven't put any numbers anywhere, but this could be a force vector or a velocity vector, but it's certainly not a unit vector. It has maybe a 10 newtons of magnitude if it's a force vector. If it's a velocity vector, maybe it's 3 kilometers per second or 3 meters per second or something, but certainly it's not 1 there. And if I want to expressly show that, I can draw this component in the x direction will be 3. Of course, that's the origin. And this component here, let's just say that that's 1, even though I haven't drawn the axes perfectly. Actually, let's just fix it real quick. Let's just fix it. let's make our vector point more like this. And let's change this, just so there's no problems, nobody gets confused. That's 1, and that's 3. So what we basically said is we have a vector pointed in this direction. It has some length associated with it, but we know that its x component is 3, its y component is 1. So just from your experience with math, you know that this vector is going to have a length more than 1, bigger than 1. All right, so how would we represent this vector? This vector right here, in terms of Cartesian notation, could be represented as 3 in the I hat direction plus 1 in the j hat direction, because the x component is 3, the y component is 1. That's the Cartesian representation of a vector. But we've already been talking about vectors enough to know that there's more than one way to write it in linear algebra. So we can write it as an n-tuple. We can say, which is just an ordered list of numbers, we can say 3, 1. So we'll just dispense with the I and j, and we just know that this goes with I and this goes with j. We put a comma, and the numbers really are representing the components in the x and y direction. So we can represent it as an ordered list of numbers with parentheses around it. But yet we can do something else. We can also represent it as capital A, 3, and 1. Right, so this is the sort of the matrix representation. Write it as a column vector, 3 in the x direction, 1 in the y direction. And so all of these are equivalent. This is how you would write it in physics, and these things are kind of how you would write it in linear algebra class. All right, now how do we calculate the length of A, the magnitude or the norm? We just did that in the last lesson, and so you should know now that the way you do that is you say, well, the magnitude of the vector A, or also known as the norm of A, is going to be equal to the square root of this vector A dotted with itself. We've done that before. And so what we end up getting is we extend the square root. We only have 2 components. When you dot it with itself, what you get is 3 squared plus 1 squared, right? And so what you end up getting, this is going to give you 9, this is going to give you 1, so what you're going to end up with is a square root of 10. And if you pull a calculator out just for giggles and take square root of 10 and truncate the decimal, you get 3.16. That's a truncation, but it's a numeric representation of the length of this vector. So if the vector represented force, then the length of this vector as we've drawn it is 3.16 newtons. If it were velocity, it would be 3.16 meters per second, whatever unit system you're using. But let's say that we want to calculate a unit vector, but we want to calculate our unit vector in the direction of A. In other words, if this has a length of 3.16, we want to calculate a unit vector that's about that big, that has a length of 1, but yet still points in this direction. It doesn't point along X and it doesn't point along Y. We're creating a unit vector that points along the direction of the vector A. And we have this definition here, we've already talked about it. A unit vector in the direction of A, that's what the hat means, is the vector divided by its magnitude. You see, because when you represent a vector and you know its components, wrapped up in that is implicitly defined the direction where the thing is pointed, right? The numbers give you the direction and the magnitude when you know the components. So when you take the vector and divide it by its magnitude, what you're doing is you're retaining the direction information, because the direction comes from the ratio of all the components, the x to the y to the z, right? When you divide it by the magnitude, you're chopping all the numbers, you're keeping the proportion of x and y and z, the ratios between them, but you're chopping the magnitude down so that the length of the thing is only 1, but yet it still points in the same direction. So now that we have the magnitude of A, it's a very simple matter to calculate this thing that we call a hat, which is a unit vector in the A direction. And the way you do it is you say, we'll take the vector A and we'll divide it by the magnitude of the vector. Now the vector A, you can write it 3 different ways. I really don't care which way you write it. You can write it as I and J, you can write it as this, or you can write it as this. But probably the easiest thing to do is just to write it as this ordered pair of numbers here. 3, 1. Perfectly fine to do it any other way, but I'm going to write the vector as 3, 1, and I'm going to divide it by 3.16. So when you look at this, you ask yourself, well, how do I proceed? How do I divide this, which is a pair of numbers divided by this? Don't forget what this is representing, 3, 1. It's representing 3i plus 1j. So if I divide this guy by a number, I'm going to divide this component and get a new x component, and I'm going to divide the y component and get a new y component. So the short answer is you take the 3 and you divide it by the bottom, and then separately you take the 1 and you divide it by the bottom. So what you end up getting is 0.95 for the new x component, and 0.32 for the new y component. So 3 divided by this is going to give me 0.95. 1 divided by this is going to give me this, and I separate them with a comma and put them in parentheses as before. But you also know that you can also represent this, right, as a column vector, right? You could say 0.95, 0.32. That's a perfectly valid way of representing this new vector. You know that this is the new x component and that's the new y component. And you can also write it equivalently, the vector, as 0.95 I hat plus 0.32 j hat. So I'm going to circle this, but you can circle this one, you can circle this one. They're all basically saying the same thing. What we have calculated is a vector, a hat. It's a vector that points in exactly the same direction along our original vector, a. However, the magnitude of this new vector is just 1. That makes it a unit vector. All right? To verify this, if you were to find the magnitude of this, what do you think you would get? Well, you should get 1, right? How do you verify that? So grab a calculator, take 0.95 and square it, and then take 0.32 and square it, add those two things together, and take the square root. You're going to get 1. So when you calculate a unit vector, you always should get a magnitude of 1. If you don't, then you've done something wrong, because that's the whole point of it. You want a magnitude of 1. But yet, if you were to plot this, 0.95 in the x direction, 0.32 in the j direction, then what you would get is a vector that would be, I mean, you can kind of guesstimate it. This isn't an exact drawing, but if this is 3, then this is probably 2, and this is probably 1. So what we're saying is it's 0.95 in the x direction and just a smidgen up in the y direction. So what it is the unit vector is going to point roughly from here to here. That means its length is 1, right? But it's going to point in exactly the same direction as a, because the ratio of the x component to this y component is the same as the ratio of this one to this one. That's all wrapped up in the definition. All we did was take the original vector and divide it by the magnitude. So we're keeping the ratio of the components, we're just changing everything so the magnitude's 1. So once you understand the concept, let's just rip through another one real quick. What if we have a vector defined as -1, 4, -2, comma 2. So that's a vector. Let's calculate a unit vector in the u direction. So a vector that points along u but has a magnitude of 1. Right? So the first thing we need to do is calculate the magnitude of what we have here. So the norm of u, or the magnitude, is the square root of, here's this component, -1 squared, plus 4 squared, plus -2 squared, plus 2 squared, right? And so what you get under here is the square root. Here you have 16. This is going to give you 4, so 16 plus 4 is 20. 24 coming from here, plus another one, 25, so you have square root of 25. And of course that's equal to 5. So the magnitude of this vector is equal to 5. Let me stop you real quick and just pause for a minute. The magnitude of this vector is 5. In the previous lesson, when I introduced the concept of a norm of a vector, we found the magnitude of a vector with 4 components like this, and we also got a magnitude of 5. But these two vectors are not the same. This vector, if you look at the different components, the numbers look the same between that example and this example, but they're in a different order. In other words, this vector u points in a different direction as the vector we did in the last section. However, it has the same magnitude. So you can think of it as, well, this vector points here, this vector points here. The length of my vector, being my arm in this case, is the same in both cases. It's just pointing in different directions. So we get the same magnitude as before, but this vector is actually different. Pointed in a different direction. But in any case, in order to proceed, in order to find a unit vector in the u direction, we just take the original vector, -1, 4, -2, and 2, and we divide it by its magnitude, which in this case is 5. So what you end up getting, when you take -1 and divide by 5, let's just keep it in terms of fractions. You get -1/5. 4 divided by 5, you get 4/5. -2 divided by 5, you get -2/5. And 2 divided by 5, which is 2/5. So we kept everything in fractional form. Of course, if you really wanted to, you could just convert these to decimals. There's nothing wrong with that. But this is a unit vector pointed in the same direction as our original vector u. It's a unit vector pointed along u. So again, in our new vector, our newly constructed or newly calculated unit vector, the length of it when you calculate should be 1. So if you get a calculator out, and if you take 1/5 and square it, and you take 4/5 and square it, you take -2/5 and square it, and you take 2/5 and square it, you add all 4 of those things together and then take the square root of the answer that you got, you're going to get 1. So that proves that this is simply a unit vector. And you just have to trust me a little bit, but if you were to plot this on some kind of a graph along with your original vector, you would see that they line up. They point in the same direction. However, the magnitude is chopped down to 1 in this particular case, and that's because the ratios of the different components with respect to one another is preserved here. We have the same ratios going on that we had here. However, the magnitude is different. So you might say, why do we care about constructing unit vectors, Jason? Why? I mean, what's going here? What's going on here? Well, you know, when you study a new course, you think back to you study calculus. There was a lot of front-loaded material in calculus that you had to understand before you could really do much else. You know, we had to learn about functions, then we had to learn about limits, then we had to learn about the concept of what a derivative is, then we have to learn how to calculate derivatives, and then eventually you get into where you can do integration and you kind of get rolling along with the core topics of calculus. But in the beginning, there was a lot of disconnected things that you had to kind of get in order to be able to get anywhere. And that's the kind of material we're doing now. We're retracing a lot of what you already know from vectors from before, but we're recasting it in terms of linear algebra, refreshing your memory also, because, as I said several times already, a lot of linear algebra is going to end up dealing with vector spaces later on. So now we're dealing with x, y, z, but in the future I may take x, y, z and crisscross them and flip them around and change the coordinate axes, and we're going to need to calculate what your vectors look like in the new coordinate system. So we're getting our bearings and kind of learning the easy coordinate systems, x, y, z, and learning the concept of norm and magnitude and unit vectors along a certain way, because all of these concepts are going to come back and we're going to revisit them whenever we learn about vector spaces later on. So that's the motivation for it. So make sure you understand this concept. We're just trying to calculate a newly constructed vector along the same direction as our vector we had, but with a length of 1. That's called a unit vector in whatever arbitrary direction we care about. In this case, we're labeling it A. So make sure you understand this. Follow me on to the next lesson where we will continue learning about these important concepts in linear algebra.